All right. Welcome back to the stream. I think we got everything set up. My name's Agent Ultra, and I'm here to program stuff in Haskell and to build stuff with functional programming and have a little fun, learn some stuff, learn some things. For the past little while, we've been building a project to try and figure out how to build a MUD. A MUD is an old precursor to MMORPGs. It was like online, real time. You connected to the same server as everybody else, but you played in text. So you sent your little commands, what you wanted your character to do, and the server would update you in real time of what was happening and what was changing. So we're going to be building that in Haskell to learn a little bit about how software transactional memory, the kind of concurrency primitives that Haskell has available for you in the ecosystem, and maybe just have a little bit of fun too. So without further ado, let's get into it. Bring up some code. Last week we were working on adding the game loop, the server ticks to the simulation, which I think is kind of working-ish. Working well enough, at least, to get us started. So let's just run the server, see what we got right now. Actually, I'm going to make sure I got the most recent code. Good, I think it's the most recent, yeah. Nothing to do. Cool. So yeah, let's run that. We should just see it say tick one every like second, a couple times a second, something like that. Bakamud. There we go. By the way, if this is your first time tuning into the stream, welcome. Totally welcome to... Okay, we are getting a little bit different behavior actually on this system. On my other system that I tested this on as well, we just get tick one, but we're getting a little bit different here. But you can see it's ticking by some values here. Anyways, it's not going to be huge press, I don't think. Anyways, yeah. So, totally brain fart there. Don't remember where I was going, but we're gonna just get into the game loop. So now that we have something of a game loop going, oh, we're showing the time accumulator. Okay, that's why it's a little bit interesting. Actually, that is kind of odd. I'm a little curious why it's showing sometimes a negative number there. Interesting. Okay, so maybe I have to fix this first and figure out what's going on here. Just to be sure, I don't have untracked files, yeah? Okay, probably not. Alright, so the game tick code here, right, is... So when we start the simulation thread, this starts in a separate thread from the main server thread. With load main, it's going to be like the main source of Lua code, for now at least. I have some ideas about how to do like an component system for this. We're using Lua code, by the way, as like the MUD code. So the idea is that the Haskell code base is going to be running the server, doing all the low-level stuff, networking, databases, persistence, and all that stuff. And game code that you write, you're going to script in Lua, essentially. So hopefully that way we can do a little bit of like, one, hot reloading, two, the game logic can be, Lua might be a little bit more accessible for game logic. I think it's fine running stuff in Haskell, of course, but I'm biased. And the other thing too, though, I think that might be a little bit of an advantage of doing it this way is that you want to iterate quickly when you're developing a game. And Haskell doesn't have like super good hot code reloading type facilities. But if we just program the game logic stuff in Lua and we have a good enough engine, then we should be able to like hot reload our Lua code and load it into our our system, and then be able to iterate quickly that way. So, might be an advantage there. Okay, so our time accumulator. So the idea with our time loop, right, is we kick off this tick function. This tick function is going to recur on itself, so it's just going to loop infinitely. The idea I think we had was that we keep track of the last time the tick ran, and we get the current time in this at the start of the function, this frame, and then we calculate a delta time. So from the current time, subtract the last time we ran through the loop, and we accumulate that. When our accumulated time plus the current delta time is greater than our time rate, that's like how that controls how fast we want to actually tick, but then we tick, right? And then we're supposed to reset the accumulated time back to 0. Update the last time. So we set that to the current time. Actually, last time, maybe that should be our current time. And then we accumulate the delta time. So let's get our update last time to be current time. Let's move current time to the top here before any of these, because every time we see atomically here, we're doing an STM transaction, which could potentially lock. Probably won't, because I don't think any other bits of the code are really going to be looking at this except for tick itself. So there's that, but just because, you know, current time. So we'll call this update, we'll call it set last time, and we'll give it current time as a parameter. So I'm going to rename that to set, and it's going to take the type of that. I think I'm just going to say it's in it maybe, and we'll just get GHC to tell us once I get that running, of course. N64, cool, no problem. Yeah, so we haven't done any of this stuff yet. So time t, or time. I'll get rid of new time there. And we'll just write time there. Okay, so we actually wanted a system time in our tvar. Let's look at our state. So we should accumulate an N64. Oh, I just don't need that function anymore, right? There we go. That's better. Okay, so we set the last time to that. Let me recompile and run. Yeah, we're still getting like highly variable numbers here. Which is really odd, because this other system I'm testing this on, one is way slower. So it's kind of interesting that I'm getting 194, negative 189. And on that system, I only get 1, 1, 1, 1, 1, 1, 1. Alright, so we should be resetting here. after we tick. When we accumulate the delta time, let's just do a little debugging here. Debug, trace send. Accumulate dt, and we'll show the dt. It's like 0, 0, 0, 0, 0, 0, a lot of zeros, and occasionally I'm seeing another blip by. Let's add a little when dt is greater than 0. It's got 1. We've got a delta time of 194 there. Okay. Interesting. These are... I wonder what could be causing them. Could it be... I can't imagine as garbage collection pauses. That's a bit much. Unless, well, I mean, I haven't really done any profiling or anything on this. We could be accumulating funks somewhere and it's just clearing it out every now and again. So it's not out of the question. The negative 189 is interesting. We mostly have 0. I wonder... Oh, this might be in seconds, too. That might be another thing. Let's look at the time library. So you can get system time. Get system time. It's usually faster than get current time. That's nice, but... Okay, system time. Right, so we get system seconds. Okay, and then we get nanoseconds. Interesting that we get a word 32 for that. That's like an unsigned UN32. Like, that's like a UN32. Okay. System nanoseconds. We can convert that to milliseconds by dividing. I think it's like a million? 10 to the power 6, yeah. So we want to get it down to milliseconds. Let's try that. Because maybe that's why I'm getting a little bit more stable on the slower system. Okay, so then current time, we got system nanoseconds, and that's going to get the system nanoseconds, and we're going to convert that. With dividing, by a million. Let's get GHCID running again. Oh, yep. It's not camel cased. Okay, so then last time as well. So I have to convert this to an int64. I think U32 should fit in there just fine. Okay. A little better. Yeah, we're getting 1s and 20 at most. So we're getting little fluctuations. Could be STM locks. Could be that we're, generating some unevaluated garbage that's getting cleaned up. That's pretty decent. It's pretty fast. Okay, let's commit that. And we're going to apply. This is going to update tick or modify tick. Simulation tick. And changing current time to milliseconds from seconds. Okay. Alright, so now that that's taken care of there, that's looking pretty good. We got to discuss how we're going to handle our objects in the game world, I guess. And maps and entities and all of that stuff, right? There's a lot to do in this realm. It's going to take a fair bit of thinking and work to get going. Okay? So, let's talk about entity component systems. Okay? Entity component systems is like an architecture, a pattern, more like a pattern. A pattern for updating a bunch of like game I think it came from game programming mostly. But it's a pattern for updating a bunch of like the state of a bunch of game objects. So let's talk about each part of that, because each entity component system, each of those words actually means a thing. It's almost like an acronym. All right. My mouse drawings are awesome. So an entity, right, marked by this entity, and my mouse writing is even better, right? Just has an ID, right? And it uniquely identifies the ID of this entity in the system, right? That can be pretty much it, okay? You don't need a whole lot more. You just need to know which entities are active. An entity is associated with a component, one or more. I guess technically we could design our system to be 0 or more, but that doesn't make a whole lot of sense, but it could. Component. Okay. What is a component? It's basically just a bunch of attributes and like properties and values. Right? So like I don't know, health. Right? 100. This might be like you might call it I don't know, life component. right? And so there could be like a relationship here where there's, you know, at least one or more, maybe 0 more. 0 more might be fine too, right? And then system. System is actually another thing, the trifecta of this thing, right? A system is basically a piece of code that's going to operate on all of the components in the whole server that are live. All right, so it's a bunch of user code that's gonna like, there's gonna be a system that's kind of associated. I don't know if they're gonna be associated one-to-one to components necessarily, but they might, they could be. Right? They could be. But the idea of the system is that it's going to go over every tick, once a tick, it's going to go through all the entities that have all the live entities in the system, in the server. It's going to go over all of the components it's responsible for. And it's going to run the code over that component to update that component's state. And all it can do is update the attributes and values inside that component. That's it. Now, why I say like maybe like not so much one-to-one is that some systems might want to have we might want to be able to have a system that have multiple components interact, right? And a system for updating those interactions. All right, so we might want a health component and a damage component, right? And so the damage component keeps track of all the hits that, say, in our combat system, this entity has taken, and then the system reads those out of that damage component and then updates the health component of that entity. Does that make sense? All right. So then we might need like potentially the same kind of relationship we have on entities here, where we have like, well, at least one. The system has to have at least one component to work on. Okay? Okay. That's ECS at a high level. For us in our server, how are we going to implement this, and like, what are we going to do, right? We could, in our simulation, like, we'd load up some Lua code. We could just make you as the mod author write all of that, or we could just give you a tick and just say, here's a couple of Haskell functions for getting data out of the database or the live objects or whatever, and you can implement your own way of doing updates. But what I was thinking of is it might be nice to have it a little bit more structured, in that the system part could be Lua. Right. Your system, whatever it is, could be a bunch of Lua code. Okay. Same with your, well, something like your component definitions could also be Lua code as well. And this will be like just a table or something like that, like a bunch of properties and some values. Although I said template because we're going to have to get into another thing in a minute. And then the entities themselves could mostly be on the Haskell side of things. You don't really have to write any code for that, in Lua at least. Right. So what I'm thinking is that we have an API for registering components, registering systems, and then instantiating entities. Okay. So let's talk about instantiation, databases, and all of that stuff. The database for this thing should keep your component definitions and your systems. All right, so your component definitions just tell us there is, in this component, there is a health level that is an integer. Int, okay. I don't know, a defense value or whatever it is. That is also like an int. Okay. And maybe a default value for these things. Maybe we could do that dynamically. Let me, instead of drawing it out, let me just do it in like pseudocode or something. Excuse me. All right, so we just need like you to give us a table, right? That just says like, okay, there's a property called health, and its value is, I don't know. Maybe it could just be an int. Maybe it's just a schema definition, right? Defense int, and status be string. Okay, something, just something, right? Okay. This is our component definition. Now, I might have a bunch of these components. This one could be like a health one. There could be an armor component. I don't know, like a movement component. Position, you know, room. Be like an int for like a room ID or something. Or if it's an AI mob or something, like it could be heading to a place, a direction, something like that. And creating an entity, we have to instantiate, we can instantiate from these component definitions. All right, so the idea of instantiating. Create a live entity from a entity template. Entity template has a list of these component definitions. Right. And we got to supply some values in order to those components in order to create the to finish the instantiation. Yeah. Pass values to fill in initial values of components. All right, so this whole process, once completed, creates a new live entity in the system, or a new live entity in the server. All right, and then once we have that instantiated, right, we've got some live systems. in there. So a system is going to have to operate on one or more components. Every tick. All right, so we're going to need a way for users to add new systems, and they're going to have to tell us what components they work on in that. So let's turn this into a bit of a design doc, I guess. The buffer, yeah. We're going to call this... Make it a markdown file? Sure. Component. These will be component definitions. All right. So, health. Maybe position or movement. That sort of thing. Right, so we got to instantiate. Actually, I'm going to call this design.org. Turn this to org mode. And I'll make this heading. There we go. Yeah, that's better. Because I want to be able to add to-dos to these. All that stuff, and we have nice handy things for it. Okay, so component definitions. We've got create a definition. We've got to have, we've got to be able to register a new definition with the server. And we have to be able to we might be able to query definitions. Existing definitions. And some other stuff, I'm sure, over time. That'll probably get us the bare minimum. Okay, systems. So we need a couple of operations on those. We need to be able to create a system. And maybe that's about it. Maybe register would be about the same as creating. Okay. Also in systems, we're going to need to execute them. And I would like to have some kind of hot reloading or reloading. So maybe at some point, this could be a little nice to have. It would be nice to update, reload this guy. Okay. So we got ourselves a little to-do list here of things we need to work on. There needs to be a sub. Okay, there we go. Then instantiating. That should be a to-do as well. Okay, so there we go. Let's work on components and getting those registered in the system. And figure out how we can make our component definitions. There's two parts actually to a component. There's like the definition, and then there's an instantiated component too. Right. So a definition just tells us like what properties there are. Health, int, defense, int, status string, that kind of thing. And a definition instantiated has a live component, has those values applied to it. So let's see, registering definitions. Where should we put some of this code? Maybe under simulation. Component. Let's also add that to our component file. Okay. Our definitions. We can... I don't know if we actually... Well, I mentioned in the doc, like, types as the schema. I don't know that I want to implement type checking. We could. Because it's like, how are we going to create a component from something like this? I could create something like a type called definition. But it's going to be not written by us. It's going to be kind of parsed from something like this, possibly Lua code. Probably should be Lua code, to keep things consistent for the user writing their game. So let's look at some Lua reference. Yeah, that should be good. Let's look at values and types, and tables are basically, I'm thinking, what we want. Stable constructors. Well, here's the trick. If we allow arbitrary Lua code for these definitions, Right, the user's going to want to know if they did something wrong. So all we want to have in such a module definition would be a file like that just looks like this. And we'd have to parse them. To know if they're valid. So we can validate them. And once we can parse them, then it's fine. Right, we know it's a valid Lua fragment of a Lua program, a Lua code that we can use for our definition. But then they can put arbitrary values in there. So I'm thinking maybe we should do it as like a DSL. And maybe the DSL should be exactly like this. And then you just write your systems in Lua. And then we could make it so that these things, once instantiated, you get like a table in Lua on the Lua side with the data of the component. Yeah, I think that would probably work. And yeah, okay. So our definition on the Haskell side of the template would just be a name for the... would just be a bag of values. It would literally be a map. No, it would be a map. No, it wouldn't be. If we're gonna define our own DSL, we're gonna have to define what types we can support, which are basically gonna be tricky to do because you might want to be able to, for example, have not just simple types here like instant strings, but you might also want objects like tables of other things, like a map. Right, and we'd have to come up with a syntax for that. Say string int. Type those as well. Ultimately, I'm going to put definition something there, but ultimately an instantiated component right is going to be basically a map, right, of like keys to something like Lua values. Actually, maybe the Lua library has something for us there. Some types we can use. Okay, so it does have a type for Lua integers, Lua numbers. Probably not stack index. Code, status code. Lua booleans, okay. They have type codes as well. Okay, integer code used to encode the type of the Lua value. Interesting. So how do we know, how does it use those type codes? That's interesting. Because if we just have a type code, that's going to be really simple for us. It's just like that one value. Let's see if I can just search for that type code. I had to play around with that a little bit. It could be like type code. No, it's gonna be a live value of some kind. So we're gonna have to define those. Maybe we support Lua int and Lua string. There's number, I think, as well. Okay, so let's imagine those are the values that we can have. We'll define equality and show for all of them. This might be decimal. This might be like text. Data.text. Let's just simply type there. Okay, something like that. And then we just map from keys to values. We're just importing the type there. Okay. All right. So then we get the component values. So a component would just be a map of these. All right, so this represents essentially like use our JSON notation, right? Like our H, and then a value might be like an L int of 100. Right, and then whatever that is, it could be like a status L string of fine, whatever you want to represent your game. That kind of thing. So that would be an instantiated component. And to go from a definition then, what is a definition? A definition would be like a map of text key to just the constructors for these, really, not the actual values. We call it L type. What is an L type? This is going to be a little bit. We have to get a little bit better with the naming here. I'm going to call it lint, lnum, lstring, and this can be vint, vnum, vstring. And so they're going to kind of have to mirror each other. Maybe there's a bit of structure for representing this stuff. And so, instantiating a component goes from a definition, and we should get, well, a component. But how do we get back a component with values? All right, we're going to need a map. We're going to need a component map, a value map, or some values to fill in, or based on our definition. Almost like we need a component. So we could write no, we need the component as input. And then what do we get back? Well, if the map values... This is basically an alias. Alright, we either get back an error of some kind or a built-in component. So instantiating is almost like validation, it looks like. Alright, just from the type alone, right? Although I think we want something a little bit more to the component, like a name. So let's make it a proper data type. We'll give it a text label and a map text value. And then we'll get our alias back of values. Alright, so given a definition, some component values, we either get some text or we get a valid component. Alright, so this could look like... let's create an example definition. This needs a constructor. And this would be basically a new type. Although... yeah, no, these should be both new typed. Yeah, new type. Alright, so the only way to get a component is to validate it. Okay, I think that looks pretty strong. An example definition. What would one look like now? Well, we're going to need to import more of map. Qualified. Alright, let's pop that over there. Now we can give tuples here. So let's try to create our example definition from our doc. Let's say health int status stir. H, and we need an L type, L int, and status, L stir, our string. Oh, we gotta wrap it in our constructor. Let's get GHCID going for us. Yeah, so we just need overloaded strings here. Okay, so that's what a potential definition could look like. Let's get our example component values. We'll map from list again. So this is where we could do h, and now we have to do the int of, say, 10, and status of, say, the string, fine. Cool. And then what we want to have is, and about, if we call instantiate, we can even put this in a test, really. We want to call instantiate with our example definition, our example component values, and we should get back a component. Well, we'll get an either component. We might get one, but we could get an error. If I try to evaluate that right now, obviously I'm going to get an exception here. One, there's no show instance component, but two, I'm going to get undefined. Because we're going to hit, we haven't filled in instantiate yet. Let's put that on there as well. Reload it. Yeah, undefined, right. Okay, so let's try and implement instantiate. Let's blow from definition the mapping. Defs and component values. I'll just write it out one conditions. Okay. So, what we want to do here, I think, in order to fill in this hole is that we want to go through our component values. And for each component value, we want to look up in definition if it exists, the key. And if it does, we want to make sure the types match. And if they do, then we can add it to our component map. Okay. So we can map over, well, if we do it as a map, we won't have the right types, because if any of these fail, like so for example type checking fails, we want to return that error at any stage. So, going into our map functionality here. All right, we can create a little wrapper for lookup that could return either for us instead of maybe. And then for iterating, we can look at control.monad. Or we can traverse over it. Yeah, we'll traverse over it. Our T of B. It's going to be the interesting part. Traverse. Have to import data.traversable. And so our first argument to traverse is some function, which I'm going to leave in now, and our traversable thing, we're going to traverse over the component values. If I flip this around, though, I could then get a function here. Yeah, so we cure here, that would be no bueno. Unless we wrap this with our component. But this is not going to work. How am I going to do this part? Okay. Sequence A is going to collect, Traverse is just going to do the actions and collect the results. What are we going to collect them into? That's the thing that we're struggling with here. Maybe we can go collect them into a map. Instantiated values. We're going to bind that, and we'll do the traverse in here. And then if that works, then we can just pure component instantiated values. It's going to traverse over the values, not the keys and the values. So we might actually need to do something from data to map.strict to do that. Traverse with key. Yeah. Okay, so this would be a function from key and value to something. Okay, now we have a hole that's either text or B0. Okay, so we're traversing over the map of component values. Now we have the key and the value in scope here in this hole. And what we're going to do is we're going to look up the key and value in the definitions map. So we're going to need a helper function for that. Although, no, I think we have one in data.either that would work. This would be the Okay, I've got a couple of things going through my head right now. I had to sort them out. So first, we're gonna look up in the definitions map the key value. Right. Okay, so the definition value type. Right. And we're gonna use a function over map.lookup. We're going to look up in definitions the key. This is going to be a do. Okay, and that is going to come from data.either. I think it's in data.either, or it's in either's package. I'm looking for something called note. Oh, it's in a different package. Dang. It might be control.error.util from the errors package. Yeah, okay. So I'm gonna need that. Control.error.util. Go to Cabal. Add that as a dependency. Where's our dependencies? There we go. Errors. It's true. 2.3.0 is probably fine. And we go here. That will be note. I don't know, we'll have a generic error here. I don't particularly like it, but we'll just get it. It's like invalid key, definition key. Or missing. Still the Cabal file. What do I do? Errors. That should be fine. What's going on? Ah, okay, better. Okay, there we go. So now we got the def type. So we have the type definition. And we have the value. So now we need to know if it's the value we're trying to instantiate with matches the def type. We can type check def type and val of, and then we can have checks match and no match. Or fail match. Another match or fail. So what I mean by that, let's create a little data type for that. Type check. And we either have match or fail, so we can either match or fail on the type check. And then we have our little type check function, right, which is going to take our component value type, or L type, definition type. Maybe this should be D type or something. And our value, and it's going to return a type check. So here we can go, okay, we have lint, and we have vint, and that means match. We have lnum, vnum, match. We have L string, B string, match. Anything else? Let's fail. Simple enough. Okay, so in the case where we do have a match, if we have a failure, we can turn left. Invalid type. And in the match case, we just need to return what are we building here? Instantiated values. A map. Okay. So in this, we need to construct this map as we go along here is what we're trying to do. We're trying to insert these values into this map. So I'm going to have to carry the map through our traversal as an argument. Or, no, yeah, basically gonna have to do it that way. Traverse is key. Otherwise, we're collecting together values. Traverse with key. Ah, it's gonna. We just have to return the B's, the values. Okay. I mistyped. Instantiated. And here is map type. Did I get lookup wrong? Oh, key goes first, then map. Sorry, I just got those wrong. Look up the key and definitions. Okay, that all type checks. Let's load it up. Let's restart the GHCF process. Yes, please. Let's evaluate our example component. Sweet. So there's our instantiated component. H is a vint of 10. The state is the vstring fine. And if I try to, for example, mess with the types here and say like the int 10 as well, we should get an error, invalid type for instantiation. Cool. I like that. I kind of really like that about Haskell, is that like sometimes I don't know exactly 100% what I'm doing. I got like a funny, fuzzy idea. And as long as you structure the types together, it kind of guides your thinking as you're going along and helps you figure things out. At least it gives you hints. Okay, so now we have this code stuff. So let's create it. Maybe we need some tests for this. Maybe this is just fine the way it is. It's almost by construction, so you really see the value of it. Maybe when we get to parsing, we'll write some tests for that. Okay, so let's create a commit for this. So we're going to add simulation / component. Yes. Adds component definitions. Yeah. Components and instantiation. Sweet. So let's go back over to that org file. So component definitions. We have a type for it. Probably add that as a type. that part is done. And we also added instantiation. Oh, I think that's under instantiate, didn't we? That's a bigger one. Good. And we save the file, this to-do file. It's pretty useful. Okay. Create a finisher type, get instantiate a component. All right. So the next part is, well, there's a couple more things actually. All right, we're gonna probably create the the component definitions as a DSL. All right, the idea of the component definition DSL is that we take parse example text. Maybe we can even maybe do like a name colon maybe that text is actually kind of nice. I kind of like that. And then we could do like int status stir. I think we're going to support tables later. We'll make this example. Into a definition. Right, so we don't have a ton of time left on the stream, but we can get started on this part. Although, maybe we don't need that component name in the text itself. Because I'm thinking that when we load these up, they're going to be loaded from files. And so we could have a convention that you name the file, and the file name will be the component name. Although, it might be useful to have the component name in this source text as well, just so you can know what you're looking at. And you might be able to format it nicely in what your file system allows. Yeah, let's just leave it that way. The other thing is because the definition itself, does the definition itself, do we add the name to it? It's just the property values, yeah. Okay, well, either way. Component, let's add the parser stuff. Let's get a little, I think we have, let's check if we have a parser library. We do have megaparsec. Yeah. Okay. Ooh, megaparsec. I gotta boot that back up in my brain to get this to work. Megaparsec. Very, very handy library. Where are we using it already? Oh, right. We have a couple commands. Maybe it parses for. Okay, yeah. Okay. Yeah. So let's go back over to components. I'm going to rename this actually to D-type instead of L-type. And there. Okay. Cradle commit for that. Modify simulation component. Changed. Renamed L-type to D-type. Probably need those. Do that. Put the parser stuff down here, maybe. Void, and we're going to be returning definition. We're going to return a text definition pair. Need data.void. Bam, no problem. Okay. Definition parser. Oh, sorry. Okay, first thing first when we parse our definition. Let's get our definition file might look like definition component name. We could force commas. We don't really need commas. We could just make new lines. We'll put commas. Keep using the same one. Status stir like that. Sake of making parsing easier, let's make commas required. Hang on. So looking at this, right, I want to be able to like have how white space shouldn't matter, just like in normal brackets. In a lot of language you're used to. But it just delineates the block of these from the component name. So the component name, we could have the file look like this. We can have a bunch of that, like a bunch of white space there. This probably... No. That would be bad. That would be invalid. Like, what is that? Should just be the text on the first line. Some number of spaces, new lines, whatever. That's fine. Ignore all those, and we get to the first brace. So the first thing's component name should be, and then the spaces at the beginning before any characters. We should also ignore those. Right. So we can skip spaces. Skim by some till skip many. Space. Okay. We skip 0 more spaces, and then we get, hopefully, a string. So we want to read all of the characters on the line till the end. So we get some till. It has to succeed at least once. So we need some kind of name. That's pretty good. So that takes parser and then our end parser and gives us a list of things. So that'll be our string. Label string. So then our character parser, our end parser. How did we do that? A command, I'm sure we've done it. We'll do take while 1p is alpha now. And then we go end of line. Do we have an end of line? That comes from data.car. Looking for no, not parser combinators. Primitive combinators. Just looking for a character tokens. One of chunk match. Yeah, satisfy. There's a performance note there, though. Oh, well, actually, that's not a bad performance note, so okay. Yeah, satisfy would probably be the right one. And we need data to car. Okay, and so let's get our label string. Next, we need to Skip many spaces. And we need to match the string, which is just our open brace. Then, so this is where we're going to need our subparsers. So we're going to get many and then we're going to need sumtil. Should you have an empty? Could you have an empty map? Component map? Or it's just a label and like no properties? Sure, doesn't hurt. It's not going to do anything probably, but so we could use manytil or there. That's going to be under a different module library sort of thing, isn't it? Under compositors. Yeah, 0 more times until we reach our end P. So these will be our defs, manytil, and it'll be our def p parser, and the end parser. Let's see. Our end parser can just be skip many spaces until we get the string match there. And def p. Then once we have those things, we should be able to here. We have to convert our string to text. Let's unpack, maybe middle string, and defs can be, it's going to be a list of tuples, which will be great for let's do it like this. Map, our component, or definition, definition, and map dot from list defs. For qualified, data.text as text, so get that in scope. And then we have to implement those parsers. Def p. And that's going to return text and an L or dval. Or dvar. D-type. That's what I meant. And def p. It doesn't return anything, just consumes its input. D5. Let's pack probably. There we go. Cool. So type checks. We still have to implement it. I don't know if we're going to have the time to, though. So I'm going to leave those undefined for now. We will commit this. Modify simulation. Component. Add definition parser. Okay, I'll commit the design. I'll leave the design doc out, actually. Keep that local for now. Gonna be updating it a lot, all that sort of stuff. Okay, so there you go. I'm gonna push this code up. If this is your first time tuning in, thanks for watching and hanging out with me. If you have any questions, of course, feel free to leave them in the chat. Always happy to take the distractions, a little backseat programming, a little bit of fun. All good. All the code you've seen tonight that I just pushed up is on GitHub, for now at least. Under Agent Ultra, that's me. And this is Bakamud. My attempt to write a MUD server in Haskell to demonstrate and learn and use Haskell's concurrency libraries like software transactional memory and its networking layer and stuff like that, to show them to you and to see if I can learn some stuff out of it and build a fairly sizable project. So far, so good. We're just getting into the entity component system, so we started designing that today, which is nice. And then we'll start integrating that once we get a little bit further along with the rest of the server. Maybe get into a little bit of persistence and stuff, because we have to do that registering and all that sort of stuff. Loading your definitions from files and all that sort of stuff too. So tune in next week. I do these streams once a week on Tuesday evenings at 10 after 8 p.m. in the Eastern Time Zone. And if you follow me here on Twitch, you can follow me here. You'll get notified when I go online. And sometimes, occasionally, I do streams outside of my usual schedule if I'm feeling a little feisty. And what else? Oh, I back up all my VODs to my YouTube channel. So if you're watching there, of course, like, subscribe, leave a comment, feed the algorithms, so on and so forth, and spread the love. And otherwise, write it down in your book, and maybe we'll see you next week. Who knows? We'd appreciate it. Thanks for tuning in and watching. May all your monas free and your types always check. Go to declarative.tv. There's a link to a Discord server there, and there's a channel for this stream. So if you think of something you want to ask, or you want to hang out with other cool people, find other streamers, check that out as well. Take care out there. Happy hacking. All the best.